Okay, so hi there. We are now in our third video in number theory, and we're still in module 1, that is fundamental properties and preliminary considerations. And this video, we're going to solely focus on the well-ordering principle. So the well-ordering principle is one important concept before we even go and plunge ourselves into mathematical induction, or the principle of mathematical induction, or in some books, simply induction. So the well-ordering principle is much needed here to give the proofs for it, and we will accept it as an axiom. So remember, an axiom is a statement that is accepted as true, even though we will not be writing its proof. It is consistent with known facts. It is often a self-evident statement, or simply, it is a statement that is obvious. So we're going to state and say here formally the well-ordering principle. So here we go. So every non-empty set, okay, so every non-empty set of positive integers has a least element, has a least element. Okay, so that's the formal statement of the well-ordering principle. So every non-empty set, so we can say that it's non-empty, therefore there is at least one element there in that set of positive integers. So this is the natural numbers starting from 1, 2, 3, and so on, has a least element. So any non-empty set of positive integers must have a least element. So as a rough example, let's give the set of 17, 23, 5, we have 18, and 13. So this set can be ordered from least value to the greatest value as 5, 13, 17, 18, and 23. So from that ordering, we can see that, and obviously, the least value, the least element in this set is therefore 5. The least element in this set is 5. Okay, so by the virtue of the well-ordering principle, we will write this shorthand as WOP, denoting the well-ordering principle. The set of positive integers, let's denote that as Z plus, is well-ordered. Is well-ordered. Okay, so that's it. And we can clearly see that the positive integers is well ordered. The set of positive integers is well ordered because the least element there is 1. Very clear and very trivial. Okay, so let's proceed to our example of one statement that we can prove using the well ordering principle. Okay, so as an example, we'll be proving this statement here. So prove we will prove that there is no there is no positive integer. Let's write that down. Positive integer. Hope it fits. Yeah, it does. Okay. Okay. No positive integer between 0 and 1. So we'll prove that there is no positive integer between 0 and 1. So clearly there is not, as from our study of numbers. But let's give a proof, shall we? So proof. Okay, so we will use the proving technique which we call contradiction, proof by contradiction, the so famous proof by contradiction, so reductio ad absurdum. Okay, so first step in the proof, since it's contradiction, we will try to give a statement. Let's make this statement false, and then we'll try to falsify that false statement, indirectly saying that this is true. So let's have, and suppose first and foremost, suppose there exists a, a in the positive integers. Okay, that is exactly, we can say between between 0 and 1. Okay, so there exists an a which is a positive integer between 0 and 1. So let's try to falsify this false statement, leaving us that this is true then. Okay, so we will let S be equal to the set of all n in the positive integers, such that, let's use the vinculum, such that this n is strictly between 1 and 0. Okay, now let's go back to our first statement. We said since we said that a is also between 1 and 0, so therefore we can say that a is inside the set S. Okay, a is inside the set S. So from this statement we can say that this set S, is non-empty. So it is not equal to an empty set. So therefore saying that it's non-empty. So therefore there has an element in S, because we have said that A is between 0 and 1, and we let the definition of S to be all n to be strictly between 0 and 1, and since A is between 0 and 1, so therefore we can say that A is inside S. Okay, so therefore we can say therefore um, by the well ordering principle, by the well ordering principle, okay, S has a least element, right? Because it's not empty, okay? And then um, it's not empty, and then it is part of the set of all integers, as we have said, we have defined, and it's not empty. Therefore, by the well ordering principle, principle, it has a least element. Okay, so S has a least element. Let's put it here. Let's call that least element as L. Okay, L as least. Okay, where we can say that L is also between 0 and 1. Okay, so again, let us see this. There exists an A that is in the integers, a positive integers between 0 and 1, and we define this set S to be all n in the positive integers, which is between 0 and 1. And since A is between 0 and 1, so therefore A is inside the set S. So therefore we have said that S is non-empty plus S is composed of all the numbers, which is positive integers. Therefore, it satisfies the properties of the well-ordering principle using this axiom. S has a least element L, and therefore this L is between 0 and 1. And we denote that this L is the least element. There shouldn't be any more lesser than this because it's the least, right? Now, remember this L. Then, um, then, or we can say but rather than then. But, oops, sorry. Try to square that L. Okay, 0. Let's have this L and then 1. Try to square this L. So remember that it is between 0 and 1. So every time, try to square a number between 0 and 1. Okay, squaring that such number will always be lesser than that L. L squared. Try to square a number, okay, between 0 and 1. Square that, you will always have a smaller number. Okay, for example, if we will square 1 half, the square of 1 half is 1/4. Square 1/3, the square of 1/3 is 1/9. The square of 1/4 is 1/16. Okay, so squaring these such numbers will always give us a smaller number. Okay, so therefore, this is true. This batch of inequality is true, and we can also say so. L squared is also in S. Okay, so again, squaring a number L between 0 and 1. Though we say to ourselves that L is an integer, but try to imagine all the numbers between 0 and 1. Square it, it's always going to be less than that L. So L squared is in S, as we said. But clearly here, L squared is less than L, okay? Which is a contradiction. Which contradicts our assumption that um, L is the least element, is a least element. A least element of the set S. So therefore, since this is a contradiction, going back to our previous statement, so we have supposed that A is in the integers, so A is in S, so therefore by the well ordering principle, S must have a least element L, so L must be the least, but we have proved that L squared is lesser than L, so this is a contradiction because we have told ourselves that L is the least, but it turns out that L is not the least, L squared is the least, so therefore this is a contradiction. Thus, um, so we have by contradiction we have told that this statement, we falsified a false statement, so therefore we have proved that there are no integers, there are no integers between 0 and 1. 0 and 1. And this is the end of proof. We'll use the QED every time we end the proof. Okay, Let me fix this. Okay, so this is the end of proof already. Okay, let's have another example. So in our module, we have another example there, another example. Prove that every non-empty set, non-empty set of non-negative integers has a least element. Okay, so let's prove that every non-empty set of non-negative integers, in short, it these are whole numbers. So starting from 0 to 1, always has a least element. Okay, so let's give a proof for this. So proof. So we will prove this by cases. We'll use by cases. So we have um, in this example we have two cases actually. So let's have case one. Or first, let's denote first. Let's define S. We will let S be the set of non-negative integers. Or we can just say let S be equal to the whole numbers. Okay, to make it better. Whole numbers, which is equal to the non-negative integers, which is equal to 0, 1, 2, etc. Okay, so let's start with case 1. Sorry, case 1. So for case 1, we will suppose that 0 is in this set S. So for example, if 0 is inside this set S, okay, so since 0 is less than n, okay, for all n in the positive integers, let's use the double script n, natural numbers, which is equal to your z positive, then 0 is less than s for all elements of s in S. Okay, so we say that 0 is the least element, is a least element in S. Okay, so that's our case 1. So for example, when we say that S is non-negative integers, so we have two cases: if 0 is inside it or 0 is not inside it. So we'll have that as case 1 and case 2. So if 0 is inside it, so 0 is clearly less than all the positive integers. So therefore 0 is less than all the S in in all S's inside this S, as we can see here. Okay, so 0 is the least element in S. Case 2. Okay, so for case 2, let's suppose 0 is not in S. Just for example, that 0 is not in S. Then S, the set of S um, be will be all S's such that all S are all positive integers, since 0 is not part of that set. So therefore, it will be, this is like equal to the, let's say S is equal to the set of positive integers, or equal to the natural numbers, shall we say. Okay, so if that happens, by the well ordering principle, here we go. By the well ordering principle, it's the set of all natural numbers and it is non-empty. So by the well ordering principle, S contains a least element. So in both cases, thus, by case 1 and case 2, sorry, by case, oh, sorry, by case 1 and 2, S, the set S, contains a least element. Okay, and that ends the proof. Okay, so I think this is a good time to end the video now. Next up, I will create a separate video for the Archimedean principle to give a highlight of it. Okay, so thank you very much. See you soon, and hope to see you in the next video. Bye.